Hello, YouTube. Hello, Room. Hello, Zoom. It's Friday. I'm in a strangely good mood. I don't know why. Um,
I'm not.
yeah. I've got the most dreadful earworms, though, which I will not share with you. Okay, so this lecture will hopefully kind of reach a milestone. So let me just find the lecture page. Nice to see plenty of people have been here already. So last week we talked about monoids, and this week we're going to talk about rigs. A rig is another kind of mathematical structure that there's a lot of about. And a rig is what you get when two monoids love each other very much. What is a rig? It's a combination of two monoids. Can everybody read this? Can you read at the back? The font large enough? Fabulous.
I don't believe it, but it's fine.
Yeah. Well, it's we're old. Yeah, we wouldn't be able to read that from the back. But we're not professors, so we're not allowed to sit in the front row reading our email. If we want to read our email, we have to sit at the back. That creates a dilemma. Anyway, we got two monoids. There's going to we're going to call them the untermonoid and the ubermonoid. And the untermonoid has to be commutative, so you have to be able to swap the inputs to the operation. And the crucial thing is that they have to have the same data, and there has to be a distributive law. That's to say, doing the ubermonoid's operation has to be a monoid map from the untermonoid to itself. And if all of this sounds bonkers, don't be afraid. You know this stuff because you've been taught it for high school. All I'm saying is that the relationship between multiplication and adding that you're used to shows up in more places than that. So you learned a whole bunch of stuff at high school about kind of multiplying out and all of that sort of thing. All I'm saying is that a rig is a situation where that stuff works. And the good news is that there are lots of those situations. And the things you already know how to do with multiplication and adding work perfectly well for a whole bunch of other stuff. And in fact, if you do CS106, you've seen that all of this sort of stuff works for and and or. Yeah? So there's more examples. So this is good news, right? That's the point about structure, is that when you find other instances of the same structure, then you know your methods for working with anything of that structure are applicable. That's why we care about noticing these coincidences, so that we actually realize that we have the tools to deal with new instances of old situations. Okay, so what I've done, I've supplied an awful lot of library functionality, and now I've just collected in this box the things we have to show to make sure that plus and times give us a rig. So here, plus is going to be our untermonoid, and you can see I'm saying it's got a neutral element 0. It's associative, it's commutative, right? And then our uber monoid is going to be multiplication. And here I'm saying it's got 1 as a neutral element and it's associative. The uber monoid need not be commutative. It might be, it might not be, you know. And the other thing we have to show is that multiplication distributes over addition from both the left-hand side and the right-hand side. And we noticed that one way round was a lot easier than the other. So this is the collection of things we need to prove. And just brought into one space. Most of them we've done already. In fact, the reason why on Monday we bothered to show you our slightly skanky definition of 2 to the power was that showing that that definition gave us a monoid map actually forced us to prove loads of the things we needed to show that addition and multiplication give us a rig. So that's the point, is that almost all of these things we've already done. I may have slightly lied to some of you, but I'm going to fix that now. About the fact, and I hope this is reassuring, that it's the end of week 4, and I have already shown you all of the Ask equipment that we're going to use this semester. What has just happened to the display? Things are on the blink. So you've seen inductively, you've seen us defining things by giving equations. You've seen us build stepwise explanations of equality using by root, and you've seen us dig our way structurally into problems using under. And what I'm here to tell you is that's what you need to know. That's the machinery. We are not going to use any other machinery this semester because that's the machinery you need to prove equations. And the only things we're going to prove this semester are equations. So you need to learn new techniques, you'll learn about some new data, you'll learn about some new structure. But as far as the machinery of Ask is concerned, it's almost all been introduced this semester, and I'm going to fix the last bit, which you don't really need anyway, just now. There's one proof technique which we have not shown you, and I'm going to show it to you now. And it's perfectly useless for you because it's how you prove something you already know. So if I use the proof strategy given and hit send, Ask is very happy. It says, yes, I already knew that. Now, pretty much by construction, I'm not going to ask you to do anything where given is useful, because why would I ask you to do things that were already done? However, this is how we do the marking, right? If you've done the problem correctly, then we try to prove the same thing. Given, that'll work. If you haven't done the proof, it won't work. So that's how we automate marking. So all I'm doing is checking off my checklist here of the things that make plus and times a rig to make sure they're all given. And if any of them aren't given, I'll get Clemens to do them. So let's see. How about let's just go for it in blocks.
What would happen if you put test, by the way?
Well, so if I put test, it would try to compute. Right. So when you say given, it looks through the collection of things it already knows and asks, is this goal an instance of it? If you say test, it looks at the definitions of the operators and tries to run them.
But would we also write it proven?
So for z plus y is y, we would, because that's one of the defining equations. Yeah, but for the other ones, not.
We would have to go into the proof again.
Yeah. So here, let's check that all of these additive things are given. And yeah, we did them already. They're all proven given. Okay. So, oops. Next up, how about multiplication? Are these three given? I mean, you might have a sense of deja vu. There are things we already did in lecture. They're already preloaded in this file. They're all given. How about...
In particular, the swap middle of
yes.
last Monday, basically.
Yes. Swap middle of 4 is very, very useful. So it was no skin off our nose to be forced to prove it. Distribution from the left. Oop. Can we spell? Send. Yep. Ask is happy with those as well. How about distribution from the right? Say given, given, we hit send, and then there's one missing. Ask says, I don't remember being given that. It's the multiplication that 0 times something is 0.
I see.
So I'm afraid you're up, Clemens.
I see. I have no recollection, but let's see briefly.
Well, think it through.
Think it through. Okay.
Why is it stuck?
Why is it stuck?
Which of the one variable in the problem are you going to do induction on?
I'm guess the Z. I'm guess the Z, but okay.
Yes.
Inductively Z.
Yeah.
Let's send this off.
Yeah. I don't have tap click. You have to actually push it. Yes. I don't have tap click because it has unintended consequences.
Okay. So once you do inductively Z, you need to do a from. The from always gives you the cases, right? In case you don't remember this.
And and then it's done. This is
magic.
It's yet another example of the phenomenon that ask gives you. You finish one step earlier than you think you're going to. So yes, what happens here is because we're multiplying 0, ask is immediately able to see that the base case is 0 times 0, which is 0, and the step case computes immediately to the induction hypothesis. So there's no problem there. So yeah, that was easy, and we're done. We've now got that.
We're given. Okay.
We now have the rig of multiplication over addition. So I want to point out to you that, as ever, the floating meeting controls are a nightmare. Your mission for next Thursday is to construct another rig with very slightly different data. So the task is to work with this type. It's called botnum. And you can see that a value in type botnum is either this thing called bot, which you should think of as minus infinity. We call that the bottom element. Or it's the constructor num wrapping up an ordinary number. So in effect, we've got all the numbers that we had before, but we've glued on an extra one at the bottom, minus infinity. So what I'm asking you to do is to construct addition and maximum for botnums. So you already have these for ordinary numbers, and you can use that. You can use the operations you have already when the inputs happen to be num this and num that. You know, if you just got num x plus num y, you just add x and y the usual way and pack that up as a num. If, on the other hand, you get you only have to say you only have to think about what ought to happen when, instead of ordinary numbers, minus infinity shows up. So here's the clue. I'm not giving anything away here. That minus infinity is such a low number that no matter what you add to it, you will still get minus infinity. Right? There's no escape by adding from minus infinity. Yeah, you know, minus infinity plus 3, that's minus infinity, right? So basically the job of minus infinity is to nuke addition in the same way that 0 nukes multiplication, right? Meanwhile, as far as max is concerned, if one of the inputs is minus infinity, the maximum's the other one. Right? You know, minus infinity is very definitely the lowest thing available. Right? So with that information, you're being asked, so here you get an empty box in which to prove things about ordinary max that you might want to know, but the plan is you should leave this box blank until you discover what you need. And then I ask you to define triple plus for, which is just, you know, I'm just choosing a different plus-like symbol for bot num, and you're being asked to define B max for bot num, and you need to check that for ordinary numbers they work, it's business as usual. And then I'm asking you to prove that there is a rig where plus is the ubermonoid and max is the untermonoid. So lots of this stuff you already built ingredients for in our first tutorial if you did that particular homework. And you can most definitely reuse that stuff to help with this stuff. But
I'm curious how you use the type constructors in the proof. Right? You say
yes.
Proof num, that means you only prove it for the number.
Yeah. Yes. So I'm asking you in particular to show that number 0 is still the neutral element for addition. Whereas I'm asking you to show that bot minus infinity destroys addition. Okay? So that's hopefully a fun one for you. And you've also already seen rigs for Boolean operations. So that's my point is that there's a lot of them about, and we'll still see more of them this semester and next semester. Also, I promise you, this machinery I'm asking you to build next week is not artificial or useless. We will need it in a couple of weeks' time. So that's the point, okay? That I realize that I've been spending the last 4 weeks leading you up the garden path. And now we are kind of stopping and looking at a bit more of the garden. It's coming together. I mean, here's another thing you might notice that our rig is our rig involves multiplication and addition. You may have noticed that our type of formula has constructors for multiplication and addition. That's to say that our type of formula is a syntax for describing computations in a rig. That is, of course, not an accident. You should also have got the message by now that even my accidents are deliberate. So there's something going on. And we're halfway through this lecture, so let's have a change of scene. Start something a little bit new, but which follows on. So this is the lecture 8 page. This is a new topic. We're starting it now slightly early. I thought we might have time to at least get going. And then the hard work will happen on Monday. I think I might switch to the document camera for a moment. So if I stop sharing and make sure that
one of the working screens is
yes, one of the working screens is on camera. Switch to document camera. I want to show you, I mean, this module is called Machines, Languages, and Computation. So I'm going to show you the workings of one of the older kinds of computation machines that human beings have cooked up. So basically, I don't know if you heard of Charles Babbage. Charles Babbage was an engineer and a mathematician who invented mechanical computation machines. In particular, he invented a thing called the difference engine, and I'm going to show you how the difference engine works. He also came up with a thing called the analytical engine, which was a general purpose computer that was supposed to be mechanical, but the engineers at the time did not have the skill to actually build the thing. It remained a design, but even just as a design, it was clear how the thing was supposed to be programmed, and correspondingly, the first computer programmer to actually write programs that could run on a specified computer happened long before we had computers. That was Ada Lovelace, who is now more famous than her father, the poet Byron. She was the first computer programmer. She wrote programs for Babbage's analytical engine. This was before men realized that computing was interesting and a pathway to political power, and started making up lies that women couldn't do it. So this is, it's the same thing with directing movies. Back in the early days of cinema, nobody thought directing movies was an important thing to do, so women did it. And when men realized that it was a pathway to success, they made up lies that women were crap at it. So, it's completely ridiculous and unacceptable. Anyway, here's how the difference engine works. The difference engine is a device for calculating sequences. So what you do is, I think I should pin this. Yeah, you start with some initial numbers. And you think of this sequence as going on forever, but the tail end of the sequence is all zeros. So there's some interesting stuff at the beginning of the sequence, and then sooner or later, it's all zeros. Okay? So these are each the first elements of a bunch of sequences that we're going to construct. And there's a very simple rule for how to take a step. It's that you add each number to the number below it. So 0 plus 1 is 1. 1 plus 1 is 2. 1 plus 0 is 1. And from here on in, it's still going to be all zeros. Okay, everyone got how this is working? Yeah, let's keep going. So I'll not bother with the zeros. So 1 and 2 is 3, 2 and 1 is 3, 1 and 1, still 1. We're still going to be 0 there. Let's truck on. 3 and 3, that's 6. 3 and 1, that's 4. 1 and 0, that's 1. And we've still got 0. Do another couple of these before we give up. 6 and 4 is 10. 4 and 1 is 5. 1 and 0 is 1. And then we're all zeros. Trucking on. Last one. 10 and 5 is 15. 5 and 1 is 6. 1 and 0 is 1. And then we're all zeros. Okay, so do you recognize the sequence that we're generating? Ring any bells? Ever played snooker? Yes, we're computing the triangular numbers. So the point is that each thing in the top row is the sum of the things below. As we go, we're making running totals. So that's what's going on. What's generating the sequence is the fact that we start from the first thing and then the difference to the next thing and then the differences between the differences and so on. So what's driving the whole thing is differences. Now, I don't know if you've ever learned the story about Gauss, the mathematician, but like a lot of mathematicians, before he became a mathematician, and pretty much while he was still a mathematician, he remained a very annoying little boy who pissed off his school teachers so much that they told him to stand in the corner and add up the numbers from 1 to 100 because they thought that would keep him busy. And what Gauss did was this. 5,050. How did he figure it out? Well, he added up the numbers from 1 to 100. And he realized that he could also add up the numbers from 100 down to 1. And if you rearrange that vertically, you add 101. You add 1 and 100, 2 and 99, 3 and 98, and so on. All of those add up to 101. So twice the answer you're looking for is 100 101s, which means the answer you're looking for is 50 101s, 5,050. You did it like that. Nice trick, but only good for adding up arithmetic progressions. You can see 1, 2, 3, 4, 5, 6. The thing we're summing up is an arithmetic progression. The differences between them are constantly 1. So also, I mean, maybe also if you learned proving by induction at school, you might have been taught to prove that the sum of the numbers from 1 up to n is half n times n plus 1. Does that ring any bells with anyone? Doesn't matter if it doesn't. My issue with this as an exercise is usually this formula is plucked out of the teacher's arse. How on earth do you come up with this formula in the first place? Never mind, how do you prove it? How do you realize that that's a thing to prove? So I'm going to try and show you a computer science way of actually seeing that stuff. Let's have another example of the difference engine at work, just to show that we're not just good for arithmetic progressions. I'm going to start with 0, 1, 6, 6. I mean, we could pick anything, but I'm picking these things. And then the rest is silence. Okay, I'll not bother with the green pen for this one. So 0 and 1 is 1. 1 and 6 is 7. 6 and 6 is 12. Should properly serif my ones. 6 and 0 is 6. Next up, 1 and 7 is 8. 7 and 12 is 19. 12 and 6 is 18. 6 and 0 is 6. 8 and 19, 27. 19 and 18, 37. 18 and 6, 24. 6 and 0, 6. 27 and 37, 64. 37 and 24, 61. 24 and 6, 30. 6 and 0, 6. 64 and 61, 125. 61 and 37, looks a lot like 98 to me. 30 and 6 is 36. 6 and 0 is 6. So this starting configuration of the difference engine generates the sequence of the cubes. And you notice that whereas previously I had 3 starting numbers and I generated something that's quadratic, here I have 4 starting numbers and I generate something that's cubic. So there's something going on and we're going to dig it out. Yes.
What magic is it because it's not?
Yes. Yes. How on earth do you figure out the numbers to start with for the series you want? That's where we're going. That's where we're going. All right. Let me go back to laptop and once more share my screen. Right. So all of this stuff, all of this chat, I did actually put in the lecture notes already. Right. Our plan, which we might just make a big start on, is for any given formula in our little language of formulae, we're going to compute another formula whose job is to tell us the difference when the formula we first thought of takes a step. So that's a lot of words. Actually, the equation that I'm asking you to prove is a much clearer statement of what's going on. You can see that we've got starting from some formula P, we're going to compute a formula diff P, and diff P's job, diff P evaluated at n, should tell us what you have to add to P at n to get P at n plus 1. So that's to say, how much bigger is P of n plus 1 than P of n? What's the step? Because what's going on in our sequences is that each row of the difference engine sequences is the difference of the row above. So we're going to explore this notion of difference. And there's something terribly important that I have to emphasize. This is going to look annoyingly like the notion of derivative or differentiation that you may have been taught at school, but it is not going to be exactly the same. The reason that it's not going to be the same is that you were taught, if you were taught differentiation and derivatives and integration and stuff like that, that is how the calculus that we use to model physics in the world of things which move smoothly. So the differences we consider are infinitesimal, and it's all about stuff we measure. Here in computer science, we don't measure, we count. And our difference is not infinitesimal, our difference is 1. So you might have learned that, for example, the derivative of x squared is 2x. Does that ring any bells? Okay. So the derivative of x squared when x is 5 has value 10. But if you look at the difference between 5 squared and 6 squared, that's 11. There's an extra 1 coming from somewhere, and it's important. So I will be blue in the face saying this over and over again. I'm going to show you where that extra 1 comes from. And then what will happen is that people in a blank panic doing an assessment will either just parrot what they learned in high school, or they'll send the problem to ChatGPT, which will also just guess it's the derivative from high school and tell you the wrong answer, at which point you'll not get as many marks. So please internalize that. In fact, over the course of CS103, I'm going to show you several different things which look like the derivative you learned in high school, but are not. Okay. This is also an example of the kind of problem that is quite typical for CS103. That's to say, where I've given you a bunch of tools that you can use, but the problems concern deployments of those tools and techniques for stuff that is just being defined in the problem, right? Questions that begin with definitions. Here's a new concept, deal with it. And very often, the point is that I ask you to prove stuff about the things that you're building. And it's the task of proving things, proving what we care about, that tells you how to do it. So let's actually make a start, because we've got a little bit of time left. I'm going to define the difference operator, the forward difference operator for polynomials, for P and for formulae. And even if I didn't know, I don't know what it is, or pretend I don't know what it is, but I know its specification. So I know I'm going to have to do work structurally over the formula, and therefore that the proof is also going to be like that. So I hit send. So at the moment, I'm not really making any choices. There's only one variable available, and I've got to look at it to figure out what's going on. And then ask gives me a bunch of goals, at which point, now that the problem's got interesting, well, I'm going to say test. And I'm not going to change these terrible names until later. So this much we can do. You notice, so here's a high-level message. You can start doing the proof before you finish the definition. Ask will still do as much computation as possible. Right. Let's also space this stuff out, just so we can think. I think we might manage to get the first 2 cases done and leave the other 2 for Monday. All right. So we now actually see the goal in front of us. We have to fix the definition so that these equations are provable. So I should say, actually hit accept, and then, yes, I didn't hit accept. That was silly of me. Right. Now I'll space them out. Right. Okay. So need a space there. Right. So our first goal is this one. We don't yet know what diff x has to be, but whatever it is, when you add it to n, you get successor of n. So do you know what it is? What number do you have to add to n to get successor of n? It's 1. So the difference in the variable has got to be the numerical constant 1. That's the shut up alarm. We'll do one more step. So now you can see, in fact, the ask is saying, what are you bothering with this case for? It's done already, right? So the goal disappears once we fix the definition to just be true, right? So Clemens, you're doing the next one. Well, it's shocking. It's like, what number do you have to add to x288 to get x288? What is the difference between a constant?
So indeed, we are trying to do this here just in case you don't see.
Yeah.
What
So we have to fix the output of diff so that adding it makes no difference.
Indeed. And so what could that possibly be? Let's go to the definition of diff. I would say we put a 0 here, right?
Yeah, the numerical constant 0.
NZ, indeed.
Yes, New Zealand.
Excellent. Now we press send. And we got the same answer, I think.
Yeah.
No, did I get the answer already?
It's that not tap click thing. Yep. So once again, the goal, ask comments out the goal says, I know this already. Indeed. Okay, so that's the deal, is we are discovering what we have to make the definition by seeing what it is we have to prove about it. It's almost like looking where you're going. It's one of those basic life skills as, seeing what's needed before you do what's needed. It's very strange because, normally the experience you have of programming is just coding away and writing a pile of shite.
Although it's a bit like writing the tests first, right?
Yeah.
And then writing the program.
Yes. So we're actually doing open eyes, deliberate programming, not rubbish. And the fun will of course start when we have the step cases. But we got a whole lecture to get that through them on Monday. Adding will take us about 10 minutes. The rest of the lecture will be multiplication. That's where the hard bit is. But we certainly give it enough for a whole thing. I should put the 1-minute papers box by the door.
Let's finish the recording. Or...
Yeah, we should.
Okay, say goodbye to
we should say. Cheerio, YouTube.